Hello friends, welcome to Learner's Planet. Friends, in this session of polynomials, we are going to discuss some graphs, zeros of polynomials. In the previous sessions, we have already discussed the basic terminologies related to polynomials, various types of polynomials, terms in polynomials, monomials, binomials, right? So, in this session, let's discuss zeros of a polynomial and their graphs. Okay, so let's begin the session. Now, a real number alpha is said to be a zero of a polynomial px if p alpha is equal to 0. That means the value of x for which the value of polynomial is 0 may be x or maybe the variable, right? So, suppose we have this polynomial 2x square minus 3x minus 2. So if we put x is equal to 2 or minus half, the value of this polynomial will be 0. That means f1 is equal to, I just put the value as 1, x is equal to, I have put 1, so 2 into 1 square minus 3 into 1 minus 2 is equal to 0. So it's 2 minus 3 minus 2, so that's not equal to 0. That means 1 is not the 0 of the polynomial, right? And if we put x is equal to minus half, so f minus half is 2 minus half whole square minus 3 into minus half minus 2. If we solve it, 2 into 1 by 4 plus 3 by 2 minus 2, right? So it's 1 by 2 plus 3 by 2, that's 2. 2 minus 2 is equal to 0. That means minus half is the 0 of the polynomial. Similarly, we can calculate f of 2 also. So f of 2 is equal to 2 2s are 4, 2s 8 minus 6 minus 2. So that's also 0. That means 2 is also 0 of the polynomial, right? Now we see zeros of a linear polynomial. In general, if alpha is a zero of px is equal to axp, then p alpha is equal to a alpha plus b is equal to 0. That means alpha is equal to minus b by a. So the zero of linear polynomial is ax plus b is minus b by a, right? Suppose I have a linear equation that is 3x minus 2, right? Now 3x minus 2 is 0. That means x is equal to 2 by 3. That means 2 by 3 is the 0 of this linear polynomial. Similarly, suppose x minus 5, maybe it is gx. So x minus 5 is equal to 0. That means x is equal to 5 is 0 of this polynomial, right? So similarly, we can calculate zeros of all the linear polynomials. Okay. Now suppose we have to calculate the zeros of a quadratic polynomial, then what do we do? Suppose alpha and beta are zeros of polynomial fx is equal to ax square plus bx plus c, then ax square plus bx plus c is equal to 0, and we will use the method of factorization to get zeros of the quadratic polynomial. I take an example over here. Suppose x square minus 5x plus 6. This is a polynomial, right? And if I have to get zeros of this polynomial, what I'll do? I'll equate it to 0, right? Now I just factorize it. So either x minus 2 is 0 or x minus 3 is equal to 0. That means x is equal to 2 or 3, right? So 2 and 3 are zeros of the given polynomial, that is this quadratic polynomial, right? Precisely, if you put x is equal to 2 in this equation, you'll be getting the x value as 0. If you put 3 instead of x, you'll be getting the value of this polynomial to be 0, right? So 2 and 3 are zeros of the polynomial, right? Similarly, zeros of a cubic polynomial. Suppose I have a cubic polynomial, maybe x minus 1, x minus 2, x minus 3, right? This is a cubic polynomial because we are having 3 power, like the cubic power of x over here. So this is a cubic polynomial. If we equate it to 0, we'll be getting the zeros of this cubic polynomial. So if I equate x minus 1, x minus 2, x minus 3 to 0, I'll be getting x is equal to 1 or 2 or 3, right? So 1 or 2 or 3, these are the zeros of this cubic polynomial. Okay? Friends, let's now discuss what is the geometric meaning of the zeros of a polynomial. Now, the zeros of a polynomial are the x coordinates, or we can say abscissa of the points where the graph of y is equal to px intersects the x-axis, right? I just elaborate it. We take various polynomials one by one to elaborate this. Now, graph of a linear polynomial, I have just drawn over here. The graph of y is equal to axb is a straight line. The line represented by y is equal to ax plus b crosses the x-axis exactly one point, that is minus b by a and 0. Now friends, suppose I take another other example, maybe x minus 2, right? This is a polynomial, or I can say y is equal to x minus 2. Now suppose if I have to draw the graph of this, I just draw it over here. Now suppose I have to draw the line of y is equal to x minus 2. So first of all, what I would do, I would equate x minus 2 to 0, that is this. That means x is equal to 2. That means when x is equal to 2, y is equal to 0, right? So this is what is ox axis and this is y axis, right? So on this axis, suppose this is the point that is abscissa is 2, right? So in this case, the value of x is 2, and when the value of x is 2, y is equal to 0. So this point is precisely 2, 0, right? Similarly, we can draw other points of the line. See, suppose when x is equal to 3, then y will be equal to 1. So the next point will be 3 over here and 1 upward movement. So it's 3, 1. Then when x is equal to 4, y is equal to 2. So similarly, we'll be getting other points as well, right? So this way we can draw the line. So this is the line which I have drawn over here. This is the point 2, 0. This is point 3, 1. This is point 4, 2 and so on, right? Now, the line represented by y is equal to axb crosses the x-axis at exactly one point. We have seen that it will cross x-axis exactly at one point. That means for a linear polynomial, we'll be getting a single 0. That means only a single value of x can make y as 0, right? In this case, the single value is 2, right? No other value of x can make y as 0, right? That means this line will intersect x-axis at only one point, and if it intersects at x-axis, the value of y will be 0, right? So this is how we represent a linear polynomial. Linear polynomial means it represents a line, right? So I hope you are clear. Similarly, we can find out the coordinates of this point as well. So at this point, x is equal to 0 because this line is intersecting at y-axis. So when x is equal to 0, y will be equal to minus 2, right? So this point is 0, minus 2, right? So this is how we can make a line. Now friends, let's discuss the graph of the quadratic polynomial. For any quadratic polynomial ax square plus bx plus c, where a is not equal to 0, if a becomes 0, it will be converted to a linear polynomial. So precisely a should not be 0 if it is a quadratic polynomial, right? The graph of the corresponding equation y is equal to ax square plus bx plus c has one of the two shapes, either open upwards like a U shape or open downwards like a reverse U shape, depending on whether a is greater than 0 or a is less than 0. That means coefficient of x square is positive or negative, right? These U shapes, we call them as parabolas, right? Now this fact is true for any quadratic polynomial. That's the zeros of a quadratic polynomial ax square plus bx plus c. Here we have c, where a is not equal to 0, are precisely the parabola representing y is equal to ax square plus bx plus c intersects the x-axis, right? Now let's see how. So let's draw the graph of y is equal to ax square plus bx plus c. We get the three cases. At max 3 cases may happen, right? Now what is the case 1? The graph cuts x-axis at two distinct points, that is a and a dash. The x-coordinate of abscissa of a and a dash are the two zeros of quadratic polynomial ax square plus bx plus c, right? Now this can be u also and this can be reverse u also. But the 2 points, that is a and a dash, in this case and even in this case, these two are the zeros of this quadratic polynomial. That means at this point the value of y is 0, right? I take an example. Suppose I wish to draw a graph of, maybe I have a polynomial px, that's x minus 1, x minus 2, right? This is a quadratic polynomial. If I have to find out the zeros of this polynomial, I equate it to 0. So I'll be getting x is equal to 1 or 2, right? Now x is equal to 1 or 2, both the values are positive. So suppose I have to draw the graph, I just draw it over here. So this is how we'll be getting the graph of this polynomial, that is x minus 1, x minus 2. This point is what? 1, 0, and this point is what? 2, 0. So if it is a quadratic polynomial, the curve will intersect the x-axis for 2 times or at most 2 times, right? It may sometimes touch x-axis also, but maximum 2 times it will intersect the x-axis, right? And the points at which it is intersecting x-axis are called the zeros of this polynomial, right? So in this case, it's intersecting x-axis at 1, 0 and 2, 0, right? So the x coordinate, that is 1 and 2, are zeros of this polynomial, right? Similarly, we can calculate for the zeros of other polynomials also, other quadratic polynomials in fact. Now suppose I have a polynomial, that is quadratic polynomial x plus 2, x minus 3, or in fact I just can say it's 3 minus x is equal to 0, right? Now I have to draw the graph of this, right? Now what happens over here? I just rewrite it, x plus 2, x minus 3 is equal to 0, and I have to put a minus sign over here, right? Now in this case, the coefficient of x square will be a negative. That means a will be negative. Now if a is negative, we'll be getting a reverse parabola, right? In this case, we were having a U shape. In this case, we'll be getting a reverse U shape, right? So now let's mark the zeros of this polynomial. See, to find out the zeros, I just have to put the value, this expression I have to equate to 0. So what I'll be getting, x is equal to minus 2 and 3, right? So this is what? Minus 2. When x is minus 2, y is 0, and when x is 3, even then y is 0. So these 2 points are where the curve is intersecting x-axis, right? So minus 2 and 3 are zeros of this given quadratic polynomial. But since coefficient of x square is negative, we'll be getting a reverse parabola. So you have to be very clear when we'll be getting this type of parabola and when we will be getting this type of parabola, right? So in these cases, we have discussed that there are 2 zeros of the quadratic polynomials and both of them are different, right? Because it is intersecting at 2 different points, right? That means it is intersecting x-axis at 2 different points. Okay, now let's see what happens when this curve touches the x-axis. Now, the graph cuts x-axis at exactly 1 point, or we can say it touches x-axis at the 2 coincident points. So the 2 points A and A dash of case 1 coincide and here to become 1 point A, right? So when it happens, I just take an example. Suppose I have a polynomial px, that's x minus 2 whole square, right? So we can say it's x minus 2 and x minus 2. Now if we have to find out the zeros of this polynomial, I'll equate it to 0. So both the values will be 2 and 2 only, right? So that means in this case, when both the values are equal, then the parabola will touch x-axis, and or we can say it will intersect x-axis only at one point, right? So we'll be having uh, two zeros, but both the zeros will be same, that's 2 and 2, right? And if the coefficient of x square is negative, we'll be getting a reverse parabola like this. Suppose it's minus 1 minus x minus 1 whole square. So in this case, the two zeros will be 1 and 1 only, but since coefficient of x square is negative, we'll be getting a reverse parabola, right? So the x coordinate or abscissa of a is the only one zero for the quadratic polynomial ax square plus bx plus c, as we have taken the example of this and this, right? You get this is x is equal to 2 and 2, and here x is equal to 1 and 1. Both the zeros are same. Okay. Now the third case is when the graph or this parabola do not cut x-axis at all, right? Here the graph either completely above the x-axis or completely below the x-axis at any point. So the quadratic polynomial has no real zeros in this case, right? Now what's the example for that? Suppose I have y is equal to x square plus 1, right? Now this is a quadratic polynomial, and I don't have even a single value of x which will make y as 0. Whatever the value I put over here, y will never be 0. Suppose I put 0, so y will be 1. Suppose I put minus 1, then y will be minus 1 square, that's 1 plus 1 2, right? So in no case I'll be getting the value of y is 0, right? So in this case I'll be getting the parabolas like this. Okay, getting my point? So there is no real values of x that will make y as 0. So in this case, the graph or the parabola will be completely above the x-axis, or it will not cut at axis at all. If it will not cut x-axis at all, we won't be getting even a single value of x when y becomes 0, right? Similarly, this case, suppose y is equal to minus x square plus 1. In this case, the coefficient of x square is negative, so we'll be getting a reverse parabola. But further, no values of, it's minus 1 over here. So further, no values of x will make this expression as 0, right? That means y will never become 0. Okay. If you put x is equal to 0, you'll be getting y is equal to minus 1. If you put x is equal to maybe minus 1, so it's minus 1 square, that will be 1, and this is minus 1, you'll be getting minus 2, right? So y will never be 0, right? So these are the two parabolas which will be getting when there is no real solution to the given equation. Okay, so we have discussed the three cases: when the parabola is intersecting at 2 points, when the parabola is touching x-axis, and when the parabolas are not touching x-axis at all, right? So two solutions, one solution, and no solution at all, right? Now friends, similarly we can discuss a graph of a cubic polynomial. The graph of cubic polynomial cuts the x-axis at least one point and at most thrice, right? So if it is cutting 3 times at most, that means at max 3 zeros will be there, right? Now we just consider the 3 cases over here. The first case is the graph cuts x-axis at 3 distinct points A, B and C. The x-coordinate of A, B and C are the 3 zeros of the cubic polynomial. Suppose we have this polynomial x cube minus 4x, right? If I factorize it, what I'll be getting? X minus 2, x plus 2, right? So if I have to find out the zeros of this polynomial, I can equate it to 0. So x is equal to 0, 2 and minus 2. So these are the three zeros of this polynomial, right? So points will be, this is minus 2, 0, this is 0, 0, and this is 2 zeros, right? So the graph is intersecting x-axis at 3 points, that is minus 2, 0 and 2. So these three are the zeros of this polynomial, that is 0, 2 and minus 2, right? So at max, for a cubic polynomial, the curve can intersect the x-axis for 3 times, not more than that, okay? Now suppose the graph cuts x-axis at two distinct points A and B. The x-coordinates of A and B are 2 zeros of the cubic polynomial, right? Now if we look at this equation, I can take x square as common, then x minus 2 is equal to 0. So 0, 0 and 2, right? So two zeros are same, that means this curve is intersecting x-axis at 2 points, that is 0 and 2, right? So further we got that at max at 3 points this curve can intersect if it is a cubic polynomial. So in this case it's 2 points, that's 0 and 2. So that's this and this. I'm sorry, this is this and this, right? So we got the 2 points. Or we can say 0 and 2, these are the 2 zeros of this given cubic polynomial, right? Similarly, if the graph cuts x-axis at one point A, the coordinates of A is the only zero of the cubic polynomial, the x-coordinate in fact. So the graph of suppose polynomial is x cube. So the graph or the curve will intersect x-axis at just one point, and that is the single zero of this cubic polynomial, right? So we discussed about linear polynomial, quadratic polynomial, cubic polynomial. Similarly, if it is a biquadratic polynomial, the curve will cut the x-axis for at most for 4 times. If it is a 5-degree polynomial, the curve will cut at most for 5 times, and so on, right? So whatever the degree of the polynomial is, we can get those many zeros of that particular polynomial. If it is a cubic polynomial, we can get at most 3 zeros. If it is a biquadratic polynomial, we can get at most 4 zeros, right? So I hope you are clear now. So let's do a quick recap. The graph of a linear polynomial crosses x-axis at one point only. The graph of quadratic polynomial crosses x-axis at most 2 points. The graph of cubic polynomial crosses x-axis at most 3 points. In general, graph of an nth degree polynomial crosses the x-axis at n points, right? At most n points, right? Maybe less than that, but maximum is n. Now friends, the important thing is let's derive the relationship between zeros and coefficient of a polynomial. Here in this case we'll be taking this relationship for a quadratic polynomial. Now what's a quadratic polynomial is px is equal to ax square plus bx plus c, right? Now we assume that alpha and beta, because we do not know the zeros of this equation since the values of a, b and c are not given. So we just assume that alpha and beta are the zeros of this quadratic polynomial, right? That means if alpha and beta are zeros of this polynomial, that means if I put x is equal to alpha or beta, the value of this polynomial will be 0, right? Or we can represent this polynomial, that is ax square plus bx plus c, as k times x minus alpha, x minus beta, right? Because x minus alpha and x minus beta, both of them are factors of this, right? But how many times they are factor, we don't know that. That's why we choose one more variable over here, that's k, or one more constant over here, right? So ax square plus bx plus c can be represented as k x minus alpha, x minus beta, where k is a constant, right? Now if we multiply x minus alpha, x minus beta, we will be getting this expression, right? Now we assumed that alpha and beta are zeros of this polynomial. Now we see the coefficient of x. That's what actually it's sum of the roots in negative, right? Sum of the zeros in negative. What was the sum of the zeros? That is alpha plus beta, right? That is sum of the zeros. And coefficient of x is what? Sum, this is actually minus times alpha plus beta. So coefficient of x is what? Sum of zeros in negative, right? That we can see over here. Similarly, product of the roots is nothing but or the constant term is nothing but the product of roots, right? Or zeros we can say. The zeros are alpha and beta and their product will be alpha into beta, so that we can say over here, right? So we can represent this quadratic polynomial in this manner, that is x square minus sum of zeros as coefficient of x plus product of zeros, right? Friends, will be doing problems based on the relationship between zeros and coefficient, but you should be clear about it before we take a problem, right? Now friends, let's make the comparison of coefficients of x square, x and constant term on both the sides, right? I have rewritten the relationship over here. That's ax square plus bx plus c, that we got this. That's kx square minus sum of zeros into x plus product of the zeros, right? Now in this side, the coefficient of x square is k. Here, the coefficient of x square is a. So, a is equal to k, right? Similarly, here, the coefficient of x is b. So, b is equal to coefficient of x over here is minus k times alpha plus beta. So, this, and here, constant term is c, and here constant term is k alpha beta. So, c is equal to k alpha beta, right? Now, this is what? K x square sum of zeros x plus product of the zeros. Now from this we can see that C a is equal to k. Now I take this explanation that b is equal to minus k alpha plus beta, and instead of k I can put a also. So b is equal to minus a alpha plus beta, and alpha plus beta is what? That's sum of zeros, right? So alpha plus beta over here is what? Minus b by a, that is sum of zeros, right? So sum of zeros is nothing but the ratio of coefficient of x by coefficient and coefficient of x square in negative, right? Similarly, from this c is equal to k alpha beta, I can put the value of k as a. So c is equal to a alpha beta. That means alpha beta is equal to what? C by a. And what alpha beta is? Product of the zeros. Right? So this is how we can get the relationship between the coefficients of the quadratic polynomial and its zeros, right? We'll be doing good number of problems based on that, but as of now you should be clear about all of these. Now what is the sum of the zeros? That's minus b by a. What is product of the zeros? That is c by a. For a standard quadratic polynomial, that is ax square plus bx plus c, right? Similarly, friends, we can derive the relationship between the zeros of a cubic polynomial and the various coefficients of this cubic polynomial, right? Now, what's the sum of zeros? That is, if the cubic polynomial is in the format x minus alpha, x minus beta, x minus gamma, k times, that means sum of the zeros will be alpha plus beta plus gamma, that's minus b by a. If I represent this ax cube, I just write it over here, ax cube plus bx square plus cx plus d, right? If you make the comparison, you'll be getting alpha plus beta plus gamma is minus b by a, alpha beta plus beta gamma plus gamma alpha is c by a, and product of the zeros, that is alpha beta gamma, that's minus d by a, right? So you just have to learn the results, because this complete elaboration is not asked in the exam, right? But you have to be clear about the results, right? So sum of the roots is what? minus b by a, and what b is over here is the coefficient of x square. What's a is over there is coefficient of x cube. So sum of the zeros is coefficient of x square by coefficient of x cube in negative. Similarly, C by A, that is sum of the products of the zeros taken two at a time. That's C by A, where C is the coefficient of x. And alpha, beta, gamma, that's product of the zeros, that is the constant term by coefficient of x square in negative. Right? So friends, in this session we discussed the relationship between zeros and coefficients of a linear, quadratic and cubic polynomial. We discussed various types of graphs over here of linear, quadratic and cubic polynomials. So in the next session we'll be taking problems based on zeros and coefficients of various polynomials. So do revise this session and the previous sessions of polynomials as well, so you feel yourself comfortable in the problem solving session. So I'll see you in the next session. Bye bye.